Cardiff University recently published a study in Science, revealing the impact of Earth's orbital parameter changes on glacial cycles. 10 years ago, our team studied the impact of solar system planetary orbit changes on Earth. Planets operate on fixed cycles, affecting and shaping Earth's components. Notable effects include seasonal plant changes, driven by Earth's orbit around the Sun. Herbaceous plants complete a life cycle annually, while woody plants add a tree ring each year. Yet people, due to habit, do not link these two celestial influences. Due to the vast variety of vegetation and challenges in data collection, we chose to use changes in Earth's atmospheric water vapor to demonstrate our perspective. All planets in the solar system move at high speeds alongside the Sun, interacting with one another while maintaining a dynamic equilibrium. To maintain balance, the various components of the Earth, while moving at high speeds, also adapt to the changes in the planet's orbit. However, people rarely connect the internal changes of the Earth with the changes in the celestial orbit. In this study, we made Earth's atmospheric water vapor as the subject, using variations in atmospheric water vapor across different timescales to demonstrate and quantify how the orbits of different planets influence changes in Earth's atmospheric water vapor. As shown in the figure, on a daily scale, Earth's rotation dominates atmospheric water vapor variations. Earth completes a 24-hour rotation cycle, while the Moon's orbit about 27.3 days, Earth's orbit about 365 days, and other planetary orbital changes are relatively minor on this timescale, making rotations the primary driver of daily water vapor changes. Variations in land-sea distribution cause differences in solar radiation intensity across regions, shaping diurnal climate patterns and associated water vapor fluctuations. Analysis shows that water vapor variation curves for consecutive days are highly similar, with minimal amplitude changes, reflecting the consistent periodicity of Earth's rotation and its stable regulation of daily water vapor. On a monthly scale, Earth's rotation completes one cycle daily. The Moon's orbit completes about 1/27.3 of a cycle. Earth's orbit advances only 1/365th of a cycle, and other planetary orbital changes remain minor. Daily water vapor fluctuations caused by Earth's rotation are minimal, making the Moon's orbit the dominant driver of atmospheric water vapor variations. The Moon's gravitational effects on tides and atmospheric circulation became evident at this scale, with its periodic changes shaping intermonthly water vapor distribution patterns, though modulated by Earth's orbital baseline, leading to inconsistent monthly patterns. On an annual scale, Earth's rotation completes one cycle daily. The Moon's orbit completes one cycle monthly. Earth's orbit advances about 1/13th of a cycle per month, and other planetary orbital changes are relatively minor. Earth's rotation and the Moon's orbit, completing multiple full cycles within a year, have stabilized effects. Thus, Earth's orbit becomes the dominant driver of annual water vapor fluctuations. Its elliptical orbital motion determines seasonal variations in solar radiation, directly shaping global water vapor distribution and circulation, and forming distinct seasonal climate patterns. On an interannual scale, Earth's rotation, the Moon's orbit, and Earth's orbit exhibit similar periodic repetitions. Their combined effects set the baseline for water vapor variations. However, differences in other planetary orbital positions emerge at this scale. Some planets complete full cycles, while others complete only partial cycles. These differences disrupt the complete repeatability of interannual water vapor changes, causing variations in water vapor distribution at the same time each year. Notably, the Moon's non-integer orbital period, about 27.3 days, combined with asynchronous changes in other planetary orbits. It makes interannual water vapor fluctuations highly dependent on the collective orbital states of all planets. This explains the variability of weather patterns, which rarely repeat exactly. Through above analysis and physical reasoning, as shown in the figure, we have concluded that water vapor changes at different timescales are primarily driven by the orbits of planets at different hierarchical levels. Daily scales are dominated by Earth's rotation, monthly scales by the Moon's orbit, annual scales by Earth's orbit, and interannual scales by the combined effects of other planetary orbits. From a spatio-temporal perspective, hourly water vapor changes are snapshots of the 24-hour cycle. Daily changes form points on the monthly scale. Monthly changes reflect stages of Earth's orbit, and annual changes are units of the interannual scale. Small fluctuations in higher-level orbits often trigger significant changes at lower levels, creating a top-down driving effect. Meanwhile, by further integrating AI deep learning technology, the trend of atmospheric water vapor changes over the next decade, and its impact on extreme climate events have been predicted. Detailed analyses and results are available in our paper. Our research team, with over a decade of expertise in this field, has laid a solid foundation for this study. We systematically investigated the overall changes in Earth's atmospheric water vapor from the perspective of planetary orbital variations for the first time, confirming the originality, authenticity, and reproducibility of the results. This pioneering work provides new insights for climate change research and aspires to gain recognition from nature.